Yeah, please, somebody was talking, but I didn't see the person.
Yeah, so
Okay, Mike.
I was able to do the that of the porosity, but I'm just sitting on it. It was a long day. I mean, so that was what I was able to do. For the porosity, uh, should I go ahead? Yeah. Okay, if you can go today.
Yeah. So, please, I'm not going to allow anybody to record, just as we did yesterday. I'm going to record, share it with Dr. Sadari, and he's going to make it available to all of us. Okay, so Mike, let's go.
Yeah, so for I think it was the porosity, that's the first one.
Yeah.
And I used the formula, the so the formula I used was for the the bulk volume of the sample minus the VS.
Okay, so
Okay,
bulk volume VT or VB minus VS.
VB minus the VS
Okay.
divided by the bulk volume. But
Okay.
in this case, we have the bulk volume, but we don't have the VS.
Yeah.
So and density is mass over volume. So making volume the subject that gives us um, uh, the mass divided by the density. And we have the WD, which is the sample weight.
Okay. Yeah.
The WD, which is the sample weight after the extraction, uh, and then divided by the density of the sample, the grain density sample, which is the 2.6.
Okay.
And that gave me the volume, the BS. And then after that, substituting that figure into the first equation for porosity, I got 19.4.
All
So
right.
the porosity becomes 23.6 minus the 19.4 divided by the bulk volume of the sample, which is 23.6. And that gave me a figure around 17, almost 18%, 17.8%,
Okay. Let me see.
0.178.
Okay. Please, any other having different solution, different answer? Okay. If there are no further solutions you would want to share with us, then we would proceed to solving it. So I want to read the question loud so that we all can go through it and then see if Mr. Michael was on the same road as we are about to use. Okay, so the question reads, "Eh, given the following data on a core sample, compute the porosity and water and gas saturation." All right. And then we are given the data that the sample weight received from the field is 53.50 grams, which is the WB or the weight bulk. Right. Now, one thing you also want to keep in your head is that in soil mechanics, they're mixing weight with mass. But don't be confused. Always use your unit to tell what you are given. All right. So sample weight as received from the field is 53.50 gram. Water volume recovered during the extraction is 1 0.5 centimeters, so which is the water content that is enclosed in the soil sample. The next parameter we were given is the sample weight after extraction and drying. So after putting it in a dry oven for 24 days to a degrees of about 105 degrees, we had this mass, which is WD or weight dry. We also have the density of the core sample, core oil, right? So now in our soil we are playing with right now, it does not only contain water, it also contains oil, right? So the density of the oil we know, or it is 0.85 gram per cubic centimeter. And then the bulk volume of the sample. So the total soil sample that we have, it has a volume of 23.60 centimeters cube. And then we have the grain density of the sample, right? So which is the density of the solid alone, which is 2.63 gram per cubic centimeter. Now let's try and attempt this question. Right. So porosity, as we know from the basic definition, it is the ratio of the void spaces to the total volume, right? So we saw that if we want the void, which is VV, total void, we want to say that it is equal to the bulk and then minus those that are contained by the solid, right, over the bulk, as Mr. Michael said, right? And then we would get VP, which is just the void or V porosity, right? So we are going to get VP over VB, right? So we are establishing that our porosity is just equal to VP over VB, where VP or VV, right? You can call it VV, volume voids. So let's use that one so that the P does not confuse us. VV over VB, right? Now, but we know that VS is the volume of the solid, which we can establish or we can deduce that from the density of the solid, right? And then we saw that the density of the solid is 2.63 grams per cubic centimeter, right? And then we know that density is equal to mass over volume, right? So now, in this question, we are playing with weight and W. So let me just go with that so that we don't confuse ourselves. So W, right, dry. Now, it is dry because it is just the solids, right? Okay. So if I want to have VS, then VS will be a manipulation of this formula to get VS equal to VD over V or rho S right here, as we are getting. Now we have the value of VWD, which is 51.05 gram. And then we have the density of 2.63, and that one too is given. So we can just put them here, and then we are going to have our volume as 19.4 centimeters. So Mr. Mike mentioned this, so that means that we are on the same road. Right. So now that I have my parameters for VS and the others, now I can come and use my porosity formula well. Now porosity is equal to VP, right? Now the bulk was also given, so we bring it here, 23.6, and then minus the VS that we got, which is 19.4, over the bulk again, which is 23.6, right? And we are going to get 0.178, or porosity in hundreds times 100, we are going to get 17.8%. which means that Mr. Michael did a great job and he had the same answer as we have. So, Mr. Michael, a thumbs up to you. You did well. Now, the next one is that you want to find a saturation. So the question says we should find the saturation of oil, water, and gas, right? So with a void, how much or the degree to which it is filled with water, the degree to which it is filled with oil and gas, right? So we break it into that component. Now, we know that S, which is saturation of water, is equal to the volume of water that is contained in the vein porosity. In other words, vein void. So you can make it VV, right? And then, but we know that the voids that is in the soil is equal to the main bulk volume minus those that are contained by solids, right? So when we take that out, you are going to get what VV is, right? Now, you want to find the saturation of water. We know that the volume of water was given. So the volume of water recovered during the extraction is 1.5 cubic centimeter, right? So it is here. We bring that one here, 1.5, and then we know the VP, right? When we take 23.6 minus 19, you'll be getting around 4.2. And then when you divide it, you're going to get this saturation for the water content, right? So 0.357 or 35.7%. So this parameter here means that for all the voids in the soil, about 35.7% is contained of with water. All right. Now we want to find the degree of saturation for the oil. Now, as water is water, the volume of water contained in the soil over the total void or VV or V porosity, the same would apply to that of the solids, right? Sorry, the oil. So oil VO over VP, right? But we know that we can't find, we were not given VO direct, so we would have to manipulate the density formula again so that we can get the volume of the oil. Now, we have V, but another one too, we were also not given the weight of the oil. We were only given the density. In other words, so we were given one parameter to find these two parameters before we can find S naught or S oil. But we know that the W bulk, right, which is the total mass, is comprised of the solids, which is the W dry, plus that which is contained with water, right, plus that which is contained with the oil, the oil plus that which is contained with air. But we established yesterday that the mass of air is negligible. So we are just going to put 0 there, which is not going to affect things over here. So now we know that the VB that we have comprised of all these parameters, and then we know this guy, we know this guy, so we can find the weight of the oil, right? Okay, now the weight of the oil will be the bulk minus that of the solids minus that of the water. All right. Now, after we finding, okay, wisdom.
When you are done, I wanted to make a contribution. So when you are done.
All right, sure. Okay, now you also want to find the weight of water, but it's not also given. We're only given the volume of the water. Yeah, Hamza.
Oh, sorry, Prof. Please, can you scroll down to the previous formula, please?
place
Okay.
here.
Yeah, this one, the total weight is equal to the WG plus W.
Over
So I want
here.
to know, yes, for the air, the weight
Okay,
of the air.
for the air.
Yeah. But if we assume that the density of the air is equal to one,
Yeah.
we will get something different from the zero.
Yes. So that is why we are not playing with density, and it's an assumption that we are making. Well, we can't have in situ we can't have a pure air. Mostly would have contained some impurities, and these impurities is going to infect the density, affect the density of the air, and it's going to play some role. Yet it's going to be very minimal. So that is why we are saying that the weight of air is zero. And then we are not factoring anything of air inside our calculations.
Okay, thank you, Prof.
You're welcome. Okay. Now, the weight of oil we have here is the total weight that we have minus the weight of the dry solid minus the weight of water. Now, we have to find the weight of water. We were only given the volume. But we know that density again is equal to mass over volume. And then we know the density of water is 1 gram per cubic centimeter, which means that the density of the water is giving us something that the mass of water is equal to the volume of water. Because when we do this and cross multiply, you're going to say M is equal to V. So the mass of the water is equal to the volume of the water. So now when we manipulate that, we are getting 1 times 1.5, and then we are getting 1.5 grams. Okay. Now that we have established the weight for all the parameters, now we can go on to find the weight of oil, right? Now the weight of oil is 53.50, which is the WB, minus the WD, which is 51.05, minus that of water, which is 1.50, and then we are going to get the weight or the amount of oil being 0.95 grams, right? Now that we have the grams, the weight, we can now go and play with the formula, which says that the volume of the oil is equal to the weight of the oil over the density. Now we were given the density to be 0.85, right? And then we got the weight of the oil to be 0.95 grams. And then when we do the ratio, we do the division, we are going to get 1.12 centimeter cube, right? So the oil contains 1.1 centimeter cube. Very well. Now we can go on to find the saturation of the oil. Now, saturation, you know that it is the volume of that substance we want over the volume of the void spaces that we have, right? So the volume of the oil, we now know that it is 1.2, that is here, and then we've got that the V or the V porosity to be 4.2, right? And when we do the division, we are going to get 0.267 times 100, we are going to get 26.7%. Now, this means that for the void spaces that are available in the soil sample, 26.7% is contained of oil, and then I think 35, right? 35% is contained with water, right? Now, but you want to note that 1 is equal to this plus that. We had some assumption that we can make the total of something 1 and play with the other parameters like VS, V total 1, WS 1. So we can also say the total of saturation being 1. In other words, since every saturation in the soil sample is just going to add up to 100, right? In other words, if you are playing in decimals, which is 1, then everybody's degree of saturation is going to fall within this 100, right? So if we have the saturation of water plus the saturation of oil plus the saturation of air. Now, we cannot ignore the saturation of air. We just also want to see that then because it is a three-phase system, we also want to see that, oh, a portion is also filled with air. They are voids in there that are filled with air and not with oil or water, right? So you want to say, you want to take your saturation of water here and then the saturation of oil, and then when you take them out of one, you are going to get the saturation of the gas content. So that is what we were doing here. 1 minus 0.375, so 0.57375, and then we have 0.267. When we take them out of 1, we are going to get 0.37. And when we take it to percentage, as we want to say the degree, and then we are going to get 37%, right? So in other words, the void spaces that are contained in the soil matter, 35% of it is contained with water, 26.7% is contained with oil, and then 37% just air. All right. So now, without being said and calculated, that is the end of the assignment, right? So we found everything that the question was demanding us to do, right? Please, any questions, any ambiguity you want us to tackle? Yes, wisdom.
Okay, thank you very much. So with this question, I started from maybe your last section, and I just want to make a contribution to the porosity,
All
because
right.
I think from that everything here is intact. I've got the same thing as you want. So with the porosity, I know that at the end of the day, since I have the grain density in this question,
Okay.
meaning grain volume will at the end of the day help me, because it's the actual volume of the solid rock particles themselves, excluding all the empty spaces between them.
Yes.
So first of all, I will calculate for my grain volume, whereby I know that with my grain volume, I have a sample weight after the extraction, which is the 51.05. So with the 51.05 divided by the grain density, will also give me the 19.410. So when I get the 19.410, at the end of the day, I will go and calculate for the pore volume, which is also the empty spaces between the grains. So that one will be the bulk volume sample minus my grain volume, which is the 23.60 divided by the 19.410, which will give me 4.190 centimeter cube. So if I divide it at the end of the day with porosity, so with porosity, my formula will be the pore volume divided by the bulk volume, which the pore, I've gotten the pore volume to be 4.190 divided by 23.60. So at the end of the day, you get the same thing as 0.1775, which is equals to, in terms of percentage, getting the 17.8%.
Yes.
17.8%.
Yes.
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 Okay.
Yes.
So, and at the end of everything, with my saturation to check if my answer is correct, which is equal to 1, which is equal to 1, I added I added 2 and I got 1.
Right.
Sorry, I'm not checking. I
Right.
added saturation for the water plus the oil.
Hello, wisdom.
Okay. Hello?
Yeah, I'm
So
listening.
yeah, I want to make a contribution to that. So maybe the remaining one I will send to you, then you check something for me. But with the I got all the answers. It just left with the where everything needs to be equal to one, so that you can see that you are correct with that. Thank you.
You're welcome. That is very nice, and that means you tried and wrapped your brains around it, and that is very nice. All right. Yeah. So that is a different approach. And please, I would wish that you would share that also with your class. And if you can explain to them also to understand, and it will be easier for them, then you have helped all of us. Okay. Okay. So the second example, but class, the first one, any ambiguities, anything that we want us to or what was the pace okay? Was I moving very fast or very slow?
Everything is fine.
Hello, can you hear me?
Everything is fine.
All right.
Yes, Doctor, I hear you.
Yeah, okay, sure. So I guess it's fine. The second example, another one to wrap our heads around. Given the following data of a cylindrical core sample, one, compute its porosity and the density of the rock grain. The second one is that the clean dry weight of the sample is 311 gram. The weight of the sample with pore completely filled with 100% saturated with a specific gravity of 1.05 prime is also 331 grams. The diameter of the sample is 4 centimeters and the length of the sample is 10 centimeters. Yeah. So we have this one on board, and then I would want to quickly do that because we have a lot to do today. Right. So when you are given this, you want to find the porosity first again. So the first thing that is we want to quote your formula that porosity, which is which is equal to VV or VP over VB, right? And now your VB was not given straight, you have to calculate it using your formula because the VB, it says cylinder. So the formula for area of a cylinder or the volume of a cylinder so that you move fast, which is pi pi r squared h, right? So now you were given the diameter, so you want to break it down to use the r, or you can move on with the diameter formula. And then you were given the length of the specimen, which is 10 degrees Celsius. So in all, when you compute, you're going to get 40 pi centimeter cube, right? Now, your VP, which is, or VV, which is equal to V total minus Vs, right? So we saw that we
Okay.
were given a total of, right? So this one, everything is contained in the second parameter, which is 331 grams. And then when it was clean, dry sample, it was 311 grams, right? So the VP is this. You bring your VB, which is 311 minus, and then you compute. Justice, please, can you mute for me if you're not giving any contribution? Thank you. So the VP being 331 minus 31, and then when you compute again to get your total void or porosity being V porosity being 19.05 grams. Oh, sorry, 90.05 centimeter cube, right? Now, yes, Prince.
Yeah, Chief, please. It seems like I don't know if I'm the only one hearing it. There's a certain kid crying in the background. I don't know if it's from your end or where, but I think
Oh,
the noise has been very consistent.
oh no, then it's not from my end. So let me check, and if I will have to mute everybody, I will just do that.
No, please.
Okay, I think everybody's muted now, and then let's move on. Okay, now that we have our VV here, we can find Bright. Yes, Bright.
Yes, please, with the VP, why are we dividing by the density 1.05? Thank you.
All right. All right. So the VP being here, a minute.
Because it's also equal to the pore volume at the end of the day. So you divide it by the specific gravity of the brim.
All right. So there are two ways to look at this. Mr. Wisdom, would you want to say yours louder before I say mine?
Yes, I was making a contribution like it is also equal to the pore volume at the end of the day. So with your VP, it will be your brim divided by the specific gravity of the brim.
Okay. 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 Right. So I want you to know that we can deduce a density formula from specific gravity. Yeah. We can deduce a density formula from specific gravity. I think that is what they did here, and then they were manipulating the formulas in order to have this here. Yeah. So yeah, that is it. So I don't want to really waste much time here. I want to try and finish. So Mr. Please, who asked the question?
Yes, I asked the question.
All right. So I want to say that you can deduce a density formula. So that is what they were doing. They were manipulating that density formula with the specific gravity, and then they were getting which we are getting now. All right.
Okay, thank you.
Sure. So porosity. Now the formula comes again, which is the VV over the V bar, right? So 19.05 over 40 pi, and we are going to get 15% for the porosity, right? And now the second one is that you want to find the porosity and the dry density, or the density of the rock grains, right? So the density of the rock grains is 311, or you're going to say the dry mass all over the total volume, right? And then you're going to get your dry grain density, which is going to be 311 all over the what is here. And then you are going to move on with that, right? So when you do that, you're going to get 2.9 grams per cubic centimeter, right? So note that density is equal to specific gravity times the density of water. And please, Bright, are you seeing it here? Note that density is equal to specific gravity. Hello, Bright.
Yes, yes, I can see it.
Yeah. So that is why we were dividing it by the specific gravity so that you can, so it's a formula, you can play with it, then you deduce your density from it. So you could have done that straight before bringing it here, but he chose to write everything. That is why you are seeing it here. Okay,
All right, thank you.
you're welcome. So another part of playing with or property of soil a specific gravity. We've heard it quite a number of times, so we want to see how they test and calculate for it. Now, you always want to keep the formula or the definition in your head that a specific gravity simply means the density or the mass of a substance to an equal mass of water being displayed at 4 degrees Celsius, where water is having that amount of density, or that where water justifies that density. That's we all know that 1 gram per cubic centimeter, right? So a specific gravity test was conducted on the sun, right? The data shown below, and then we want to calculate the specific gravity. Now, you want to note something here. Now, we were given the mass of the pycnometer, and this one is a bottle like, I don't know how to, like this. Some small bottles, yeah, pycnometer, and then we put the sand, we put water, those process we go through in the laboratory, and then it has a mass of 38.2 grams, right? And the mass of the pycnometer and dry soil is 64.3 grams, right? And then the mass of the pycnometer, dry soil, and water shoots the value to 154.8 grams. The mass of the pycnometer and water is 138.5 grams, right? So you want to note all these things, the key words where it says dry soil and water, where it's at the pycnometer and water alone, where it is the pycnometer alone, because we are about to deduce a formula. This formula you want to put somewhere, right? Because this is one of the easiest questions you can get for all the marks, right? Because they're just going to take the masses and play with them to have a result. So given mass one, mass of pycnometer, the second one is mass of pycnometer and dry soil here, mass of pycnometer, dry soil and water here, mass of the pycnometer and water, which is also here. Now you want to calculate. You always want to keep the formula in your head that it is the mass of the substance to the mass that was displayed by water, right? So something like that. So you want to say the mass of the solid or the substance that you are playing with. So you want to have that mass aside. So mass of the dry solid is M2 minus M1. Now you want to go and check M2. M2 is the pycnometer and the dry soil. And then M1 is only the pycnometer. So when you take M1 from M2, you are going to just get the mass of the dry soil, right? Because you are taking out the pycnometer out and we are only going to get the dry soil, right? And then when you have that, you put it somewhere, and then you are going to say this M5 here, mass of water displaced by soil particles, which is M4 minus M3, which is the mass of the pycnometer, dry soil, and water, right? Plus M soil again. So when you sum those parameters up, you are going to get this, right? So MS was equal to 26.1 grams, and then taking everything out so that we can see how far the solid displayed the water, right? Which we are going to get 9.88 grams, right? almost almost 9.81. We have been saying it. All right. So specific gravity now is the mass of the substance over the mass of water that is displayed by the soil, right? And then we're going to get this division, and we're going to get the specific gravity here. Now it is dimensionless because the mass and the mass here are going to cancel out. Yes, wisdom.
Which the third one, M3.
M3.
The mass of the water in M3. Why not M3 minus M2? But he said M4 minus M3. When the pagnometer contains soil plus water.
Okay, so you're asking why I'm not
Why
saying
not
M3 minus M4, but M4 minus M3.
why not M3 minus M2?
M3 minus M2.
Yes.
Why? And you are trying, what do you want to find? Let's see what you want to find, why you are going to say M3 minus M2.
No, I was
Because
just
when you subtract M3 or M2 from M3, you are going to take out you are only going to left with the water. Now, see, it is not the grams of water contained there. It is the mass of displayed water by the soil particles. Now, we are going to have let me just try and narrate how this test is conducted in a laboratory. We have the pyranometer there, and then we put soil inside, we measure. We put water inside the soil plus the pyranometer, we measure. Now we put all the three and then we measure. We want to see when we put only the water will be still at one point. The moment it is water plus the solid particle, the water is then going to move, right? Or it's going to increase in mass. That is why we are saying that it is the water, the mass of water that is displaced by the soil particle. Please, am I making sense, Wisdom?
yes.
All right.
Please, can you touch on it again? It's not so clear.
Wait, what I just said.
Yes, yes, please.
All right. So I was narrating how the process is done in the laboratory. So we put one. It doesn't matter where you start from. You want to measure your pyranometer bottle so that you see how much it is affecting your system. You write it down. You want to put only water inside and you measure. Then you write that down. You put water plus the soil and the pyranometer. Then you measure. Now, after that, you want to see how much or what is the marginal difference between the only water and the water plus the solid particles or the substance which you are measuring its specific gravity. And then when you check that displacement, that margin between them, that will be the water displaced. And the ratio between that mass content and the water displayed would give you your specific gravity. Hello, Mike, are you getting it?
Because I was the formula, the M5 formula, that is what it was a little bit confusing me. I was thinking that so there's the pyranometer, there's water in it,
Yes.
and then we want to see how you want to quantify the displacement of water.
Yeah.
So the moment you add the how do you call it, the M3, that
Mhm.
should change the volume of water. It will displace the water to a certain level. So I'm just a little bit lost with how the MS is coming in. That's what is, because already the M3 captures the dry soil and then the water.
Right.
and the
So
pacnometer.
when you try to perform this math, you should be getting a negative.
Yeah, the M4 minus M3. Yeah, that should be negative.
Right.
Yeah.
So the
Okay.
MS,
Dr. Hussein, meaning your last point of the M5, you accounted for about three steps in one.
Yes, that's
That's
what the
what I'm
precision
getting.
is.
Meaning your last steps of the M5, you accounted for about three steps, making it one.
Mhm.
Because with the first step, I would have gone by the way of maybe the mass of the dry soil. So after getting the mass of the dry soil, I also meaning the M2 minus M1. From there, then I also check the mass of the water in the M3, which is the mass of the pagnometer and the dry soil and water. Getting the M3 minus M2. After that, then I come and check for the mass of the water in M4. Meaning at
Yes.
that point, I'm checking for the pagnometer full of water, only water. Then the next step, the mass of the water equal in volume to solid. Do you get it? So from there, then I also check for my gravity. So meaning I'm getting your point. Meaning with the M5, it is combination of about three steps, making it one.
yes.
Yeah.
Okay, I get it. Thank you.
Okay. Please, I saw others raising their hand. Let me
Yes,
check.
sir. So I was also thinking that to get the mass of the water displaced by the soil particles, we can subtract the M4 from the M3 because we have the mass of the pagnometer, the dry soil, and the water. So if you have M4 as the mass of the pagnometer and water, if you subtract the M4 from M3, it should give you the dry soil.
Yeah, but our goal here at M5 is not to find the mass of the dry soil. Yeah, you can also manipulate and you should be getting this same thing over here. I don't know if I'm making sense to you.
Okay, so
Yes,
you are looking for the mass of water displaced by the
Displaced.
soil particles.
Yes.
Okay. Okay, I get it now. Okay.
Okay. Okay.
now, Mr. Hussein, I wanted my brother to come back again because I don't get his submission. Because if
Okay,
you are
I think he
subtract
was
the M4 minus M3, mean at the end of the day with the M4, you have a mass of pagnometer and water, and the M3 is mass of pagnometer, dry soil, and water. So even with the M3, you are having three different kinds of volumes. Do you get it? So it is rather maybe the mass, the M4 and the M3, whereby you are going to get only the mass of the dry soil, because definitely the mass of the pagnometer are going to cancel, and with that, no, even with it will be the 3 minus 2 minus 1, so that you get only the mass of the dry soil. But if you are trying to say M4 minus M3, I don't get it. Unless you come back again, then explain to me with that.
All right, Desmond. Okay, Desmond, let's go. You'll be the last person to talk. We spent much time here.
So, my question is the mass of the water displaced by soil particles. Why can't we subtract M2 from M3? Because M3 is mass of the pagnometer, dry soil, and then water. So if you want the mass of water, we subtract that of pagnometer and dry soil. That should give us the mass of the water
But we are not finding the mass of the water. That would have been
displaced.
very right. We are finding the mass of the water
Placed.
placed by the soil. I don't know if I'm making sense to you.
Yes, exactly.
Yeah,
I can you use some just for clarity, because if you can use some drawings to just do a little sketch for, because I think people are lost here.
Sure. All right. So what I'm trying to say is that I'm thinking of You would get this one better if you have seen how it is being done in the lab. Because no matter how I explain, you would want to interpret it as it looks here. But if you see the video of how it is done in the lab, you would appreciate what the formula is saying here. So I think having much time to explain this thing over and over again, I would want to give it as an assignment so that you go and look at how the test is done. When you see how the test, when the person is putting this, taking it out, you can further then come and appreciate this formula. Please, so pardon me that I'm not going to do that because our time is almost up and then we are far. Yeah. Yeah. Please, if you would agree to me on that because we have almost exhausted 2 hours and then we are just on about 2 slides.
Well noted.
Sure. Right. So when you perform that calculation, you're going to get your specific gravity. Now we have another phase relation calculation on board here, and it reads like this. A container of mass 2.83 cubic millimeter, right? And then it weighs a mass of 9.81 newtons, or the weight. The dry sand was poured to fill the container. The container and the sand weighs 52.3 newtons. Calculate A, the void ratio, and B, the porosity. Describe the condition of the soil, whether it is loose or dense. Assume that JS is 2.7. Right. So with this problem we have here, quickly I want to go through. You want to have your container and then it is filled with sand. You put your sand inside the container and please a minute. Hi. Hello, can you hear me?
Yes, please.
Can hear you.
All right. So when you put your sand into the container, the weight of the container in the sand is going to be influenced, right? And so you're going to have something like this here. And the weight of the dry sand, the weight of the dry sand is also given as this. So if you want to find only the sand, you want to take the container out of the container plus sand, and then we are going to have this one, which is 42.5 newtons, which is equivalent to 0.0425 kilonewtons, right? Now, the step 2 is that it says calculate the void ratio porosity. So void ratio and porosity, you come and see if I know my void ratio, I can easily calculate for my porosity, right? So calculate the dry unit weight first, because when I get the dry unit weight, I can manipulate the formulas in order to attain anything that I want. I can manipulate the formulas to get anything that I want. So I want to find my dry density here, and I'm going to do it as the weight of the solid over the total volume, right? And then I know that the weight of the solid is 0.0425. There is a typo. And then the total volume, which is 2.7. 83 times 10 raised to the power negative 3, right? And when I do the division, I'm going to get 15 kilonewtons. Like I gave an example yesterday that mostly your dry will be getting around 15. And if you are to work for the bulk, you should be getting around 17 or something. All right, so you can put that in your head. So you calculate for the void ratio. Now that I have my dry, I have about 4 formulas which I can get for dry. And based on what I want to use the one with E so that I can manipulate the formulas to get my E. So yesterday we established this formula as our 12th, the 12 formula, right? And then when you perform your calculations, you're going to get your E being 0.64, right? And then now that I have my E, I can straight away go and find my porosity, which is E over 1 plus E is equal to 0.7, and then I can have my that. Now, the fifth one, which is one of the new things we are encountering today, is describe the soil, right? So these mathematical calculations have their implications, right? And then we have a chart here to help us. We have a chart here to help us interpret this soil, right? So it says that from the table, N is about 43%. So when we check the chart, we will see that N is about 43% and it lies between the medium dense or firm, right? Medium dense or firm. So I would say that then my soil sample that I have is a sand and it's medium or dense or firm, anything that I want to put it, anywhere I want to put it. But you will know that it is a medium dense or firm soil. Yes, wisdom.
Please, can you move up? I want to check something. Okay. Meaning the void ratio. Okay, I'm fine.
With a void ratio.
No, I wanted to check. Meaning there's no need for you to calculate for the volume of the void, but you can
Oh,
go straight away and calculate for your void ratio.
yes. So that is why
Okay.
yesterday I gave that 12 formula so that you don't have to go and calculate this volume, this volume, this volume, and then be struggling with time. So that you can play with the 12 formulas and then you go your way. So we saw this yesterday, which was the 12th formula.
Thank you, boss.
Right. So there is another question here, which we are also going to solve. I just want you to be conversant with the phase relations questions because most of the time soil mechanics comes with this a lot. So a sample of saturated clay was placed in a container and weighed. The weight was 6 newtons, right? And the clay is in its container was placed in an oven for 24 hours at 105 degrees Celsius. The weight reduced to a constant value of 1, right? The weight of the container is also 1. FGS is 2.7. Determine A, the water content, B, the void ratio, C, the bulk unit weight, D, the dry unit weight, and then another parameter, which is a new guy here, which is the effective unit weight. But we have seen it yesterday in our formulas. It was around formula number 5. So let me try and find. Sure. So here, so the effective unit weight, here is the formula. Sorry, number 8, formula number 8, which is equal to JS minus 1 all over 1 plus E gamma water, right? Okay, now let's move on and see how we can play with it. Now, you want to find the water content, but a bit tricky. You don't just start because it's going to just trick you. Now, you want to find the actual weight of the soil that you want to use, right? So the first one, like I said, write down the given parameters, right? So the weight of the sample and the container is 6 newtons. Weight of the dry sample plus container is 5 newtons. Now, determine the weight of the water and the weight of the dry. Now, the weight of the water is 1 newton. So you take that out. The weight of the dry now falls to 4 instead of 5. Now you want to know that 1 is for the container and 1 is for the water. And so if we have 5 newtons of, sorry, we have 4 newtons, it is a result of we also taking the container out, right? So this is the parameter we are playing with, right? A lot of students get confused with this type of question. They think that once they take the container out, they should be playing with the 5. But depending on what you are playing with, if you are taking the water out, then the dry soil should be 4 because the water has been expelled. Now, to determine the water content, we established a formula that W is equal to WB minus WD all over WD, right? So you can also say WW over WS because when you take the solid or the dry particles from the bulk, you are going to get the water content or the water mass over the soil, and then you're going to get the water content in percentage. Right. Now that we have the water content, let's see something here. What is the second parameter to find? The void ratio. The void ratio. Now, with this question, you only have one parameter, which is the W, from all these 12 formulas. There is not a single one that demands only one parameter. Right? So you'd have to just see the question and also think through again. Now you want to recheck the question and see what else was given. Okay, we were also given the GS, but one thing you have to, sorry, I think that was it. Okay. You also want to see you were given the GS, which is 2.7. But one thing you have to also note that they gave you another parameter by saying that a sample of saturated clay. Saturation means that the degree of saturation is Saturation means that the degree of saturation is 100 or it is full. The soil is full. And so it is contained fully of water. And so the degree of saturation is 1. So now with that being established that S is equal to 1, then we can go to our almighty formula. We can go to our almighty formula and use it because it says that SE is equal to WGS, right? Now, I know my S being 1 because it is saturated soil sample. So I can say E is equal to WGS, right? I know my E to be I know my W, sorry, to be 0.25, and I know my GS to be 2.7, and I'm going to have 0.675 as my void ratio. Now that I have my void ratio, I can have my porosity, which says that N is equal to E over 1 plus E, and then I can have my porosity 2, right? So with that, you go through okay, having this guy here. Now, the next thing is determine the bulk unit weight. Now, since I have E here, I can go with all the formulas that have E that can find the bulk unit weight, right? And also, since I have my dry, because we found our dry unit weight. Did we do that? All right, that was with the previous question, right? Since I can find my bulk because I have a lot of formulas here, I can say that my bulk unit weight is equal to is equal to GS plus SE over 1 plus E gamma water, right? I know my GS to be 2.7 plus SS is 1, E is 0.67657, right? And then I have my 1 plus E again, 6.7 times 9.81, and then I can have my bulk, right? So when you compute that, you see they used a different formula. We also used a different formula, and we should be getting the same answer, right? Now it says the next one is to determine the dry unit weight. Now that I have my bulk unit weight, I have formulas to get my dry unit weight, and it says that gamma dry is equal to gamma bulk over 1 plus E. Now, having my gamma bulk to be 19.7 plus 1 E, I'm going to get my dry being 15.8 kilonewton per meter cube. All right, so are you checking what I said initially? The bulk is 19.7 and the dry is 15. Right. So since these questions are being recycled over time, make sure anytime you are given some things, like be checking your answer with these notes, right? Be marking them with these notes. Hamza, sure, Hamza.
Please, Prof. I don't know if it is a mistake from my side, but the formula I have here is gamma B over 1 plus W.
Gamma B,
Yeah, over 1 plus
1 plus
W. Because
W.
yours is 1 plus E.
Oh, yeah, sure. Sorry. Thanks for that. Yeah. Thanks, um, Hamza. All right. So these are the steps. Every other time you want to write your parameters and see what you have. See that you have read through the question to see all the hidden parameters, and then you will know what next to do. All right. So the next one is to find the effective unit weight, right? And then I would want to explain effective unit weight a bit. Effective unit weight is that unit weight that is really causing the harm, or that is really affecting the system, right? Now we are just saying bulk unit weight because in situ, but we can have some instances where not all the things that we see are affecting the system. But the effective unit weight means that that portion of the unit weight that is really affecting everything, the system that is going on there. Right. So the effective unit weight goes with this formula GS minus 1, 1 plus E. And then when you substitute in what you've calculated, you're going to get your effective unit weight. So for the bulk unit weight, that was saying 19.7, and the dry, which was saying 15.8, it is just 9.9 kilonewtons that is affecting the system, right? You can also say that the effective unit weight is the saturated unit weight minus the unit weight of water. And then you can also put this one, but like I said, you can write as much of formulas that you want, but that 12 formulas has everything inside, and then you can play with them to be getting everything that you want. All right. So please, any questions, contributions, um, yeah, so that we can move on. Okay, if there are not questions, I'm going to give an assignment, but this one I'm going to take them and use them as assessment. So I'm going to make it available to the rep through Dr. Sadari, right? is going to make it available to you. You are going to work it. I would like that you write it, and then I'm going to mark it. You write and scan as a PDF, and then you send it to a mail that doctor is going to provide. I'm going to go through all of them, mark them, and use them as an assessment. All right. So that is basically that for the phase relations, right? Some questions are really challenging. Others would are very just normal ones. Others too. But the more you practice, the more you get your hands familiar with them. And every rock mechanics questions or exam is flooded with these type of questions. So if you don't get yourself okay with writing solving these questions, it's going to have a big time headache on you. All right. So we have some time, so I want to continue. All right. So we are going to a different physical property, which is permeability. Permeability, right? Permeability is that characteristics of the rock or any substance that allows something to flow through it, right? So geology would have the definition like this. It is the interconnected pore spaces in a rock that allows water to pass through it, right? So interconnected pore spaces, right? We can have pore spaces in a rock, but if they are not interconnected, they are going to be just holes. So we have, let's say there is this very porous rock, which is called pumice, right? And this pumice has this shape, have this structure with a lot of holes on it. The moment these holes are not connected to each other inside the rock so that it allows water to seep through it. So we are going to come across something called seepage, right? The water is not being allowed to pass through these holes and out of the rock, then it is not permeable. The moment it allows it to run through these holes and then get out of the rock sample, then the rock is permeable, right? So permeability is a characteristic for assessing the ability of rock to predict the flow of fluids, right? It is a property of a porous material to permit the passage of fluid within interconnected voids. It is only those that are interconnected inside the rock sample that will allow the water to flow. So look at this figure here. A rock, is it a concrete? Yeah. And then they are pouring water on it. And then there is water flow at the bottom of the rock, right? So when there is this water flow, that means that the holes began from the top and then they were connected through the soil or the rock particle, and then the water is being let out, right? So when this is happening, the ability of the rock to allow this water to pass through is now termed as the permeability of the rock, right? So porous rocks such as sandstones usually have high permeability, while granites have low permeabilities, right? So they are saying that quantitative definition of permeability was first given in an empirical relationship between the between some parameters. We are going to really look at them. And it was developed by this man called Darcy in Germany, 18
Shaman.
in 1856, right? And it says Darcy's law states that the rate of flow, the rate of flow, rate means how fast something is occurring per time, right? So the rate of flow per unit area. Now, when we take a rock sample, a circular edged rock sample, and then we pass some water through this, the rate at which the water is going to be dissipated out of the rock, right, per this area that we have been given, it is what Darcy is saying. It says that the rate of flow per unit area per unit time is proportional to the gradient of the pore pressure at that point. Now, we call something hydraulic gradient, right? Hydraulic gradient. It is that difference between potential of the rock, right? Or that point or that tilt. Now, we all know that water always is a lazy, my lecturer will say, water is a lazy medium or a lazy guy. He will always want to move from the move freely through the place where he thinks it is convenient, right? The moment water will flow, that means that he has gotten that path, right? And then we all know that the moment something is lying flat like this, when you pour water on a flat surface, it's going to stay on it. The moment there is a tilt, there is an angle, there is a gradient between there is a gradient between the surface and where the water is going, then you're going to see that the water is going to flow, right? So that's he says that per unit time is proportional to that gradient of the pore pressure at that point, right? So how much water is moving from this pore space is as a result of how much incline, how much gradient there is at this point of the rock, right? And then Darcy proposed a formula that says that K is equal to Q mu, the length, area, and then the change in the pressure.
2212. 2212.
Daniel, please, if you're not contributing to the class, kindly mute yourself. Right. You are saying that where K is the coefficient of permeability, right? It is measured in millidarcy. Where Q is the volumetric flow rate, which is in centimeter cube per second. Where U is the viscosity of the flowing medium, which is in centipoise, right? And then we have the length of the flow path, which is centimeters. We have A, which is the cross-sectional area, and the flow path, right, which is the cross-sectional area net of the flow path, which is centimeter squared, and change in P, which is the pressure differential, which is in pascals, right? So you want to keep this formula, right? You want to keep this formula somewhere, that coefficient of permeability. If we are saying that a rock has a higher coefficient of permeability, that means that this is the flow rate. He allows much of water to flow through per time, and then its viscosity is the viscosity of the flowing medium is higher, and then the length to which it is traveling or the gradients which is traveling is much favorable. That is why we are going to say when K is higher, right? And then if K is lower, that means that this area, the change in pressure is also higher, right? As the formula is depicted. Okay, so there are three types of, yes, Wisdom.
So I want to ask if assuming K is negative, what does it mean?
Wisdom, I can't hear you.
I want to ask, is assuming K is negative. Please, can you hear me?
Yes. Okay.
Yes.
Okay.
You made mention of the flow rates. So I want to ask, is assuming K is negative?
To the point that we get to K being negative, that means that we'll be having K at 0. if you're having K to be 0, that means that there are not any space that any medium can be flowing through. So I don't think there will be a case to be having K to be negative. Then that soil particle would be perfectly impermeable or impervious. It will not allow any fluid to go through.
So that this formula applies to when there's a flow from a higher head to a lower head.
Yes.
Okay.
So that is why Darcy, he says that it is proportional to the gradient. So there has to be hydraulic gradient before, or the change in head, as you say, before there can be a flow. Please, am I making sense?
Thank you. Yeah.
Hello.
Yeah, Thompson.
Yeah, I want to make a contribution. You
All
see,
right.
when you look at the Darcy formula over there, we have K is equal to Q, U over L, then the A delta P.
Yes.
So anytime you have the delta P divided by L, it gives you the gradient. That's the gradient that we are talking about. So
All right.
if you have the delta P over L, it gives you the gradient that we are talking about.
That is very nice. So let me add this. I was skipping, but since okay, so
I don't know. Please,
this
I don't know. Hello, Mr. Say, I don't know if this is the exact formula for the Darcy law, because I know of Darcy law making it volumetric flow rate, which is the Q, equal to the negative of the K, which is the hydraulic conductivity. So that at the end of the day, it's going to multiply the remaining values. That's why I was asking if the K, when the K when the K is negative, I wanted to know the meaning of that. So I don't know if with this, because the other literatures with the Darcy, the most or the acceptable formula doesn't start with K with me. If
yeah,
I stand to be corrected too. I stand to
sure,
be corrected.
sure. So the Darcy formula range, that is why I'm saying, since this portion of this lecture is not going to dive too much into permeability, I would have taken my time to prove from that very first point to this very first end of arriving to this formula, right? Anyways, there can be other further studies, but I have not come in contact that K is negative, right? So this formula is actually manipulated. And as Mr. Um, the man who just Thompson said, anytime we have L over change in P, it is actually L over change in H. L being the X, the change in P, which is the change in pressure from the higher pressure head to a lower pressure head. That is when water will flow, right? So this change in P is actually change in H, right? And with this change in H, we can say that it is the Y component to this matter, and then the L here being the X component to this matter. That is why we are saying the hydraulic gradient. I don't know if I tackled your question well, Mr.
Okay,
Wisdom.
thank you. Okay, Doc, thank you.
Let me come in small. So wisdom. Usually we can also have negative in the Darcy formula. It just indicates, let's say higher pressure to a lower pressure.
Lower pressure.
That is the interpretation of the negative there.
Yes.
Yeah.
Thank you.
Thank you.
Oh, okay. All right, that is fine. Okay. So we move on. So we are saying that there are three types of permeability. We have effective permeability, absolute permeability, and relative permeability. So effective permeability is the ability of the rock to conduct a fluid in the presence of other fluids in the section, right? And they're saying that it functions at the saturation level of the fluid, right? So the higher the saturation level, the higher the effective permeability. It is the ability of the rock to conduct a fluid in the presence of other fluids, right? So let's say we can liken that to an affinity, but this rock, I have an affinity of making water pass through me and disallowing the others, right? So the effective permeability of me to water is what is being expelled here, right? And then we are saying that it functions at the saturation level of the fluid. The more there is the fluid that I am having high affinity towards, that I can allow to pass through me, the higher the saturation level, or the more I would allow that fluid to pass through me. Okay, so the second one is relative permeability. It is the ratio between the effective permeability of a given fluid at a partial saturation and its permeability at 100% saturation, known as absolute permeability. So K permeability is okay, how much can I really allow the hypothetical, right? How much can I really allow fluids to pass through me, right? And then how much am I allowing some fluids to pass through me? The ratio between these two would bring me something that is called relative permeability, right? Or so we say that Kr is equal to Ke over Ka, right? So that is with relative permeability. So continuing. Permeability is affected by temperature due to changes in viscosity, hydraulic gradient, and grain shape packing. Now, grain shape and packing can be talking about the density, right? And then viscosity here, the moment the temperature starts to rise, every or almost all liquid or fluid becomes less viscous and they begin to flow, right? And then the hydraulic gradient, right, forcing its ways through because when there is pressure, it is temperature change, there is some force that is going to move and all those geological instances, right? So small grain reduce permeability and increase porosity and an increase in porosity increases the permeability but not directly proportionate. Now, like what I was saying, or the instance I gave when I started, that there is a rock which is highly porous, which is called spumice, and there's another one which is called scorial. Those are tough rocks, right? Tough, which means they are formed by volcanic ashes, and then they are very, very porous, right? Those rocks having a lot of spaces doesn't mean that they are highly permeable, right? They can have those holes over there, which were actually caused by bubbles when volcano were cooling bubbles, and then they left, and then the things that were kept inside, the gases that was collected inside, left, right? And so this guy having those pore spaces does not mean that it is porous. Anyways, there is higher chances that because it has many holes on it, a lot of them would be interconnected to allow water to flow. So small grains reduce. Also, we have something with clearly particles. They don't allow water to pass through them because they are highly packed. And if they are like this, if the grains are a bit higher, then closing them will have a lot of void spaces. But when they are smaller, they tend to fit in, leaving less spaces in between the soil particle. That is why we are saying that small grains reduce permeability, right? And then we're also saying that the increase in permeability does not proportionate that it is going to have higher permeability, right? So permeability conveys information about the degree of interconnectivity between pores and fissures, right? So pores, we know they are holes, and then fissures are cracks that do not have offsets, right? That is a geological definition. They have cracks all over, and when they can interconnect, then they would be giving out the ability of the rock to let pass water or fluid pass through them, making them highly permeable, right?
Hello,
Okay.
sir. Please check small grains. The spelling small gains.
Oh,
I
all
think.
right. Okay. Yeah. That is a
Yeah.
typo. I'm going to resolve that.
Thank
Thank you
you.
very much.
Hello, hi.
Yeah, Mr. Broby.
Sorry, sorry. Please, there's an emergency. I have to step underground.
Oh, all right. All right. All right. All right.
Thank you.
Please make sure you bring us gold.
Okay.
Okay. Okay. So permeability conveys information about the degree of interconnectivity between the pores and the fissures, right? So I explained that. It has bearing. It has bearing on practical problems, right? Pumping of water, oil, gas into or out of a porous formation, storing fluids in mines, predicting water flow in a tunnel. So I know quite a number of us work in a mine, and I would want us to share some of the problems you get with permeability and seepage. So anybody, because I know when you have tailings and then the chemicals which contains sometimes cyanide and all those chemicals be seeping through the waters and then having its way into our water tables, causing a lot of contamination in the environment. You get to have high blood pressure. Please, can anybody share with us one problem which they encountered in their workplace about the rock or the soil matter they being permeable?
Doreen Dochi.
Mr. Wisdom, come again.
I know of a lady called Doreen. She's in the mining environment, so maybe she can share some with us.
Yes, Mrs. Doreen, please kindly share some information because this is one headache that really affects the mind. Miss Doreen, are you around?
We are marking attendance.
Okay, it seems Miss Doreen has vanished. All right. Okay, so this permeability most of the times help us. Okay, justice.
Stop snitching. Wisdom, stop snitching.
I wanted to say Portia. So, Doc, you can call Portia too. He's working on a TSF.
Oh, okay. Portia,
Yes,
kindly share
big
with us.
TSF.
Justice, please, a minute, please, before Portia, Justice, your hand is raised.
What's that? Okay.
Okay, if Justice is not talking, Portia, kindly let's hear you.
Please, my network was bad. I didn't hear the question.
Okay,
heard
I'll
everything.
repeat. Don't worry, I'll repeat. So, in a mine, what are some of the instances that the permeability of the rock or the medium that you are working with affecting you, like giving you a headache? And Portia's network is off
Okay, so
again.
maybe I would say maybe for drilling.
Okay.
No, it's the once if it's very permeable, it makes the water move freely and to be on the surface of the floor, which sometimes affects it if maybe proper drainage system is not done to channel them to a sump or something.
Oh, okay. Yeah. 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 Thank you very much. Yeah. So I've never been to the mine. My lecturer used to tell me, or yeah, my lecturer used to tell us that when they are having holes, they are drilling holes. Sometimes the mine plans that we'll be going with explosive, which is only comfortable in the dry places or dry lands, right? And now you drill the place and then you have water being in your holes. You didn't plan for emulsion or those water liking explosive that can work over there. Then you would have to have an extra course draining or dewatering that blast holes, and then that is causing extra time and money and others. So I saw another hand. Yeah, no.
Yes, sir. So as I said, as you were talking, I just wanted to add like in stoves when you are after drilling the hole, you see a lot of water inside and like charging it with this explosive, like using amphor becomes very difficult. So these are some of the issues sometimes it affects the mind also.
All right. Thank you very much, Joseph. Wisdom.
Yeah, I wanted to verify something on what he said. As my brother just said, it depends on the uh, explosive or the chemicals you are going to use. They get it. So
Okay.
sometimes if either water or without water and you are using emulsions and other stuff, you can still blast. But in terms of doing blasting and doing drilling time is when we at least try to pump the water out or get some so that we can accumulate the water at one section so that it will reduce and prevent caving of the hose. Sometimes
Okay.
the hose then cave. So if you pump in the explosive, it won't get to the charge and everything affect the blast. But before that, let's also switch to underground in terms of the permeability and everything. The deeper you go underground, then the stresses and the heat and everything, the pressure and everything down there increases.
Yeah.
So it's going to a point the rocks them feel like they are sweating. So the deeper you go, the more you are going to have like weak walls because of the porosity and everything. You see, the more there's a pore in the rocks, it also weakens the rocks because at the end of the day, that movement uh, causes another or has another influence on the rock faces. So when you get to that section, what the geotech or the rock mechanics people do is to increase their support system. You get it? Because if you don't increase your support system and you see that there are a lot of porosity going on, there are a lot of movement of fluids or water from the rocks, at the end of the day, it can easily collapse. It's like water at the back of your wall, trying to push, trying to push, trying to push. If you don't take care of it, one day you come and your wall will be down. So that's an example of an underground tool. The deeper you go, you try to increase your support system so that the porosity in that section can also be reduced. Thank you.
Eh, Thank you very much. Okay, Justice, you want to talk?
We had an experience in one of the pits that we were working. So what
Okay.
happened was you let the drillers drill. It's a surface mine, surface
Okay.
operation. So the drillers will drill, let's say, 10 meters. And
Just if we can't hear you, please can you increase your volume?
yeah, can you hear me now?
Yeah, go ahead, senior.
Yeah, so it's one of our surface operations. So what we realized was if you assign the drillers to drill, let's say 10 meters, you come and the holes are around 9.5 and 9 meters. So initially we thought it was the drillers who were not doing the right thing. So we decided to have an experiment. So the moment they drilled, we did a hole dipping. So let's say 10 meters, you achieve the 10 meters. We waited for like 4 hours. We'll go back. I realized that the 10 meters gradually was getting to 9.8. By the following day, we were around 9.5 to 9 meters. So we had to do some studies and realize that yes, because of the fishes within the hole, that was what was contributing. So within the hole, it was washing sediment to the base of the hole. And one thing we also realized during the blast was anytime we did a preload, you came back and you did your final stemming height check. You can see that the final stemming height has also dropped in terms of a preload. So these are some of the things that the permeability of a rock also can influence in terms of your drill and blast activities.
All right. That is very nice. That is interesting. Wow. Okay. So thank you very much for your contributions. And um, I want to quickly take us through some others. So what Justice said and what Wisdom said. So Wisdom, the more you go down, the more your geothermal gradient increases. That says that at every 10 meter, if I can remember right, your temperature was going to increase by 11 degrees, which is going to increase also the pressure. And unfortunately, we also have water tables underground. So the more you drill into these water tables, and you are not lucky to find these highly permeable rocks, they'll be letting water seep through to your holes, right? And what Joseph said, these permeability or permeable rocks can also swell, which is one parameter we are going to see
Hello,
next.
Mr. Isaac.
Madam Portia.
Hey, we are loaded though. Our head is even making us. Please do the example tomorrow, we beg.
Okay.
Unfortunately.
Please, did the class agree to that?
Yes, sir.
Yes, sir. Yes,
Yes.
sir.
All right. Then I will let you have the assignment, which you are going to solve them, take a shot or scan them into a PDF format and deliver them to a mail that Doc is going to provide. I'm going to sit down, look through, mark all of them, and then I will use that as an assessment. Okay, so let's take note of that. So let's be expecting it, right? Okay, so
Okay.
since I see, okay, the hand is off. Please, any questions, contributions?
Isaac, some of us were having network problem only today that but we will try and do our best.
Okay. So I think Doc will share the videos in which is going to really help you. And I think Doc has a YouTube channel which has quite a number of these lessons over there, which you can go and then have catch up with the class, right? So if there are not further contributions,
So please, when are we supposed to submit
So,
the assignment?
please, yeah, the assignment. I wanted to find out, is it possible you can share it with us on the platform, the WhatsApp platform?
yes. So that is why I'm saying that Dr. Sadari himself is going to relay that assignment through your class web, and you're going to have it. It will come with a link where you're going to submit them through, and the dates and the deadline for submission.
Thank you. Thank you, sir.
All right, you're welcome. Okay,
Thank you
so
very much for understanding. Yeah.
thank you too, for sure. All right, so if there are not further contributions,
My network was distorted. Please, the submission date.
oh, the submission date will come with the question. So
All
when
right,
you
all
have the
right,
file, you have everything on it.
all right.
Okay. So thank you very much for joining, and then I'll see you, God willing, tomorrow. So have a great evening and goodbye.
Please, tomorrow is Saturday. Are we going to
Doc,
meet?
tomorrow?
Oh, sorry. Then Monday, sorry.
All right. Thank you.
Monday we are going to church.
Choose from over 200,000 vehicles online. Get your... The Lord gave me these ideas.